there is a method you can use to solve. Yeah. So in the textbook, if you go to page 53, you can find the idea, hint, solving that question. Yeah. So here, let me, oh, sorry. Here, I like to show you the method on the textbook. Okay. And see if you are doing the right way. Yeah. All right. So here, let me end the slideshow. All right. End the slideshow. And go to, all right, question 13. Yeah. The reason question 13, it's a long nonlinear equation. Yeah. Y prime cube sine y. So that's a nonlinear one, right? That's hard. Y double prime nonlinear. All right. Yes. So if you use the normal way, it's hard. Yeah. Because in all our method, we didn't cover this one, how to solve this one. So it's quite special. Yeah. All right. So another thing, yeah, before I will show you the solution, another thing I want to show you. Yesterday I posted answers, solutions for exercise 2AB solutions. So you may not have time to take a look. So here I show you one solution that is helpful. So hope you can, you can download. Yeah. Here I open that PDF file. Yeah. This one, solution file. Okay. All right. Solution file. There is one question closely related to this one. Look at number 18. Look at this question, number 18 here. Number 18, y double prime equals 1 plus y prime squared, nonlinear, right? Nonlinear, okay? Oh, sorry, not this one. Yeah, not this one, sorry. Yeah, this one, can be solved easily. Look at number 21. This is relatively hard. Number 21. Y double prime equals parenthesis 1 plus 1 over y, y prime squared. This equation nonlinear. You have y double prime, and a y, similar to your homework question. Nonlinear, y prime, double prime, y, no x. This method, you cannot have x. If you have an x, then that trick won't work. Yeah. So only y, no x. Okay, that trick would work. Yeah. So here, you can see in the solution, I let z equals y prime, z equals y prime. Then y double prime, I use the chain rule to represent in this way. This is the key part. This is the key part. Yeah, I'll explain. This is the key part. Because after z, then we can find a solution. Okay? Then we can find a solution. Yeah. So you can study this solution. Yeah. Here, I do not go through this solution. Yeah. But I explain another one. Okay? So that one you study at home. Okay? Yeah. And you can use the same method to solve your homework question number 13. Number 13. But here, I want to explain clearly. Yeah. Otherwise, if you see my solution, the hardest part is you may not understand here, right? If you can understand this line, yeah, you're almost there. Okay? You're almost there. Although I write explanation, but I don't know if you can understand. All right? Yeah. Yeah. So here, I show you in our textbook. So this is our textbook. Page 53. Look at that, page 53. Textbook. All right. Reduction. Show that So this is the f function. You have y, y prime, y double prime, but you don't have x. If you have x, then it doesn't work. Can be reduced to a first order ODE with y as the independent variable. Y prime equals this expression, then z equals, where z equals y prime, derived by the chain rule. Yeah. So here, the example I give you, I took from here. All right? Yeah. So number 7 is your homework assignment. Number 7. Okay? Yeah. Number 10, I just solved. Number 21 in exercise 2AB. Yeah. I solved. Okay? All right. Here, I like to show you solve number 5. Yeah. Number 5. Yeah. Here, I show you right here. Okay? All right. To explain this method. Yeah. It's nonlinear. Yeah. Number 5. Yeah. Yeah. Here, let me use. All right. All right. All right. Yeah. Here, let me show you how to solve number 5. Okay? Yeah. So, number 5 on page. Yeah. Question number 5 on page 53. Okay? The question is y times y double prime equals 3y prime square. Yeah. That question. Nonlinear, how to solve? All right. First, we let z equals y prime. That's okay, right? Yeah. So that's simple, the step. Yeah. But the next step, that's the hardest part. Yeah. Z here. We have a z function. Okay? All right. So this z function, y prime, usually we treat this z as a function of x, right? Z is a function of x. No? The variable is x. Okay? All right. So now the harder part is, can we treat z as a composite function? Yeah. Here, composite function view. Yeah. Here we need to take composite function view. Yeah. So, you know composite function, right? What's the composite function? H of x equals f of g of x. This is a composite function. Okay? F parenthesis, inside parenthesis, there is another function, gx. So f composite g to get hx. That's the composite function. Okay? All right. So here, we use this composite function structure to understand the z function. This time, z is a composite function of 2. So what is the z? Okay? All right. Z, so what is zx? Z, we composite. Z inside parentheses, we use y of x. That's our composite function view. Okay? Inside parentheses, there is another level. We use y. Okay? Y of x. So g, we take this composite function view. Okay? Yeah. Yeah. Because it helps a lot. This view change helps a lot. Because this you can write z of y. Here, this y is a variable. See? Z here, z of x, but here you can treat y as a variable because y you treat as an intermediate variable. Because y, eventually, y is a function of x. Composite function, okay? Yeah. All right, so here, the key step is you take this special view, z as a function of y. Okay, all right. After you take this, then, because we can simplify y double prime a lot. Y double prime. What is y double prime? Okay, y double prime is it d over dx of y prime? Is y prime equals this? Derivative of y prime, but with respect to variable x. When you take derivative with respect to x, right? Yeah. That's the meaning of y double prime. Okay? All right. Now let me write. Is it, because y prime equals z, is it dz over dx? Is it dz over dx? Right? Yeah? Based on assumption, z equals y prime. So we replace y prime by z. All right. Now, because z, look at here, z is a composite function. When we take derivative of a composite function, we can apply chain rule, right? Chain rule. Yeah. When you take derivative for composite function, we apply chain rule. What's that? dz over dy times dy over dx. That's the chain rule, right? Through the intermediate variable y. Yeah, we insert intermediate variable y. How about that? Okay, chain rule. You're familiar with chain rule. Yeah. Okay. Yeah. Just do it in this way. All right. Now, dz over dy, we keep it. What is dy over dx? Y prime, right? What is dy over dx? Y prime, right? Y prime is z, right? So, y prime is z. Z times dz over dy. Okay? So that's y double prime. This expression, the good thing is, x is gone. You do not have x. Okay? You do not have x. X is gone. Okay? Yeah. Let's go back to the original equation. Let's go back to original equation. Okay? Yeah. So what's that? Y times y prime. Y prime is z dz over dy equals 3z squared, right? Can you see this new equation? dz squared. Is this simpler one than the original? Can you see it's simpler than the original? Yeah. All right. Do you have confidence to solve this one? Yeah? Confidence to solve this one? All right. Let me just say a few more words here. To solve this one, can you cancel out z both sides? Can you cancel out z both sides? Although you can, but before you do the cancellation, you need to take z equals 0 to see if it's a solution. Is this solution? Z equals 0. Is this solution? Yes, right? So keep this solution. Z equals 0 means y prime equals 0, right? Means y equals constant c. Okay? So you have a constant c solution. Okay? So you can check in the original equation, constant c satisfy the original equation. Okay? So you don't keep that constant solution. Then you can cancel out. Because you already counted. Okay? Then you can do the cancellation. Y times dz over dy equals 3z. It's separable, right? Separable, okay? Yeah. So dz over z equals 3 dy over y. Can you solve this equation easily? Natural log, easily, right? So after you find the z, can you go back to solve, because y prime is that z. Can you go back to solve that another separable equation? You can find the solution y. Okay? That's the trick. Okay? That's the trick. Yeah. Question? Yes, yes. Yeah. Final answer include that C. Okay? That simple one. Yeah. Yeah. So I didn't try your, homework assignment one, but this method should work. Yeah. So you have this example here. Also, the solution I gave you, question number 21 in that exercise 2AB, that one, another example. So you have these two examples to help you solve that question 13 in your homework assignment number 1. Yeah. Okay. Yeah. Yeah. Compared with the older solutions, now you can see it should be different, right? So I guess it should be, because this method, I cannot find this method myself. If I do not look at the, hint in the textbook, I do not know how to solve myself. Yeah.
So for this method to work, it has to have like z equals 0, y prime equals 0, and y equals c. Those all have to be true. Is that what you were trying to say?
Oh, z equals 0? Well, oh, this is a special solution. Yeah. Because here, when we cancel this z out, before we cancel it, we need to consider z equals 0 case. If this could be a solution. Yeah. So here we consider this case. We consider this case. Yeah. Yeah. So after we cover this case, then we can assume z non-zero, then we can cancel out. Yeah. Otherwise, we may throw away a solution. Okay. If you don't consider this case, you may lose a solution. That's the problem. Okay? Yeah, we don't want to lose any solution. Yeah. Yeah. All right? Yeah. Hope you can do well in that homework question. Yeah. With these two examples. Especially the hard part is that chain rule part, that composite function view. I think most of you may not feel comfortable on that composite function. Yeah. How can we do it in that way? Yes, we can. Yeah. Z is treated as a function of y, y is a function of x. So then z as a function of x in a composite way. Yeah. So that means, understanding, yeah. Concept understanding is useful here. Yeah. If you understand that composite concept, composite function concept, then you can handle this special technique. Yeah. All right? Yeah. All right, so let's move to next topic. Yeah. 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 So what's that? Yeah, that part of C. Yeah, that part of C. Part of B. So we will finish part B quickly. So let me just finish it first. All right. All right. Yeah. So we are at the bottom. So we're at the bottom. We're here. So we are in the inverse part, right? This step. Yeah. Next, we need to find A inverse. The question, how to find A inverse? Right. So for the A inverse, there is a formula. 2 by 2 matrix inverse. There is a simple formula. Yeah. Yeah. All right. Yeah. The formula is A inverse equals 1 over determinant of A multiply a 2 by 2 matrix. Yeah. The 2 by 2 matrix, if you compare with the original matrix, diagonal entry, you swap 2 entries diagonal. So A11, A22, you swap those 2 entries. And the other 2 matrices, you do not swap, you take a negative sign. Okay? That's the way you write 2 by 2 inverse. 2 by 2 inverse. Okay? All right. Now let's apply this formula to calculate our current 2 by 2 A matrix. Yeah. 2 by 2 matrix, determinant 1.6. So 1 over 1.6. Then diagonal entries, we swap 2 entries along the diagonal, 12 and the negative 2, not 12, 1.2 and negative 4. So 1.2, top left corner, negative 2, bottom right corner. Okay? The other 2 entries just take opposite, minus. Yeah. Multiply negative 1. So that's the inverse 2 by 2. Okay? All right. So A inverse, we have this 1. So then JP equals A inverse negative A inverse minus G. So we do it on scratch paper. So we get it. JP equals this vector, 3, 0 vector. That's the way we find this JP vector. Particular solution, JP vector. Yeah. After we have this JP, we can write the general solution for the non-homogeneous system. Non. Yeah. All right. So the last step, general solution, JH plus JP. Yeah. With C1, C2 to be determined by initial condition. Initial condition, J vector as 0, 0, 0. Yeah. By the assumption, 0. Yeah. Yeah. All right. So you plug in, that's a 0 vector. Yeah. So you can find the C1, C2 value easily. Yeah. C1, negative 4, C2, 5. Yeah. So then the final solution, so we can write the final solution in this way. Yeah. That's how we solve this non-homogeneous linear system. Okay? Yeah. Study this example. Yeah. How to solve non-homogeneous linear system. Yeah. It's a 2 by 2, not that hard. Yeah. If it is a 3 by 3, then a little harder. Yeah, 3 by 3. Yeah. Think about. Yeah. All right. Yeah. So we finish part B. Yeah. So this is part B. Yeah. All right. Next, let me jump to part C. Part C. Sure. Part C, non-homogeneous linear systems of ODE. C.1, constant coefficient systems of ODE. Yeah. Easiest case, constant. Yeah. All right. Homogeneous linear system of ODEs, n-dimensional this time. Yeah, not 2 by 2. Yeah. So we need to consider the general case. Yeah. But idea the same. Yeah. All right. So here we assume a matrix with constant entries. Yeah. So consider a solution with the form. Yeah. Yeah. Here we, we go back to the beginning. Yeah. Beginning. So this time, yeah, here, actually, you can see this. When we find a general solution, we actually, from this is a vector form equation, differential equation. And here you can see we can recall our first class consider decay model, right? Decay model, it's not a vector form, it is a scalar form, right? Scalar form, is this the decay model, right? Decay model, then we consider our solution, it takes this form, right? Some constant times this E function. Yeah. So that's our, but here, we generalize from that decay model, okay? Decay model, yeah. So we use this special type of solution, and here we generalize from that scalar y to vector y. Scalar coefficient C, here we use a vector coefficient x. That's the difference. In the generalization, we extend from scalar to vector form. That view. Yeah. All right. So you can see the structure. Yeah. Structure difference. All right. With x here, a constant vector. Yeah. X vector does not contain any t variable. So it's a constant vector. Yeah. All right. Then y prime equals lambda times x times that E function. All right. Yeah. And also, yeah, that y prime, because if you plug into the original equation, you get that. Yeah. So you can see, basically, you need to solve an eigenvalue problem. You also need to solve eigenvalue problem for the general case. Okay? Yeah. So the general case, the key assumption, here we need to make key assumption. Yeah. Because in linear algebra, the whole theory could be very complicated. Yeah. So here we cannot go through that eigenvalue, eigenvector, that whole theory, very complicated. So here we take a relatively simple case from linear algebra. Relatively simple case. So what's the simple case? The key assumption, we use this assumption, we only consider this case, the simple part. A has a linearly independent set of n eigenvectors. So this is the case, much simpler, structurally much simpler. So we want to consider all the possibilities under this assumption. Under this assumption. If this condition is not satisfied, then our solution could be very complicated. Okay? So we don't want to go that far. Right? And the good thing is it covers most of the real world applications. Yeah, not 100, but 90 something percent. Okay? Definitely not 100. 90 something percent. Yeah. So, all right. So this is a simpler case. Yeah. Most applications have this property. Yeah. So we just take it. Yeah. All right. Under this condition, yeah, we want to see because under this condition, there are several cases. We want to see those cases. Yeah. Case number one, how do we get this linearly independent set of eigenvectors? The first case, when A has n different eigenvalues, then this condition must be satisfied. Okay? If A has n different eigenvalues, that condition must be satisfied. Okay? Here we do not prove it. It can be proved. Yeah. Mathematically, it can be proved. Yeah. But here we skip that proof. Yeah. Linear algebra, the full course, yeah, you will see the proof there. All right? Yeah. Yeah. But here we just use the result. Yeah. We don't prove it. All right. Case number two. A, where A is a symmetric matrix. You know symmetric matrix, right? Symmetry. Symmetric matrix. Okay? All right. So what's the symmetric matrix? Yeah. Here, let me write the meaning of symmetric matrix. Let me use diagonal matrix. Oh, sorry. Let me use a 3 by 3. 3 by 3. Yeah. Because for the symmetric matrix, diagonal, oops, yeah. Oh, yeah, because the battery runs out. Yeah. Runs out. I just. All right. Yeah. So the diagonal here, because diagonal, you just imagine you put a mirror on the diagonal, okay? Put a mirror. So then other entries you flip. So should be the same, okay? So A12, A21 should be the same. These two entries must be the same. Yeah. Because they are symmetric with respect to the diagonal line. All right. So then this one, A23, and this one, A32, they should be the same. Okay? Then this corner one, A13 and A31, they should be the same. Yeah. So we call it symmetric matrix. Okay? Yeah. Yeah. So when A is a symmetric matrix, we have the property. Yeah. Yeah. So the general expression is this. Yeah. A JK entry, J row K column entry equals A KJ entry, K row J column entry. Yeah, so that's the expression for the symmetric matrix. When A is a symmetric matrix, you have this property. A has linearly independent set of n eigenvalues. Yeah. That can be proved. Okay? Yeah. Here we do not prove it. Here we just use the result from linear algebra. Yeah. We don't prove it. All right. Case number 3, A is skew symmetric. Yeah. Some people also call anti-symmetric, skew symmetric. Yeah. So not exact symmetric, but you take a negative sign. Okay. Yeah. Not symmetric, but after you flip with respect to the diagonal, you need to change its sign, opposite sign. Okay. Opposite sign. So minus AKJ. That's called a skew symmetric. This type of matrices, we also have the condition A has a linearly independent set of n eigenvectors. Yeah. Yeah. So with these 3 cases, these 3 cases may not cover all of them, but these cover most of that case. Yeah. Not all of them. Yeah. So that's what I say. The whole eigenvalue, eigenvector theory could be very complicated. Yeah. 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 Right. 1, 2, 3, automatically we have this condition. Okay? If you have any one of the 3 cases, we automatically have our assumption condition. Okay? Yeah. That's simple. That's simple. Yeah. Yeah. But that may not be 100%. Yeah. Here we do not say it covers all the cases of assumption condition. Yeah. Yeah. Because still there is small portion not covered. Yeah. These 3 special cases, yeah, do not cover. Still, yeah. But we won't go, that much details. Yeah. All right. After this preparation, yeah, then, yeah. All right. So here there is another thing. Yeah. Case number 2 and case number 3, even you have same eigenvalues. Yeah. Because eigenvalue, you may have, what do we say? Multiplicity of roots, right? Multiplicity of roots. Yeah. For case 2 and case 3, we allow the same rule repeated multiple times. So multiple roots. Yeah. Yeah. But case 1, only single roots. Case 1, we do not allow multiple roots. 2 and 3, we allow multiple roots. Yeah. All right. Yeah. Double, triple, quadruple. Yeah. Ample. M multiple. M multiplicity. Okay. Yeah. Double, triple. Yeah. K multiplicity. Yeah. That, like that. Yeah. All right. So then we have this eigenvalue, eigenvector relationship. Yeah. All right. Yeah. So now you can see. So from now on, we assume we take the conditions, special cases from this slide. Okay. Yeah. For the remaining of this class. Yeah. Yeah. Relatively simple case. Yeah. Yeah. Otherwise, too complicated. Yeah. All right. Basis of solutions and the Wronskian. Yeah. Yeah. Still, this time we consider basis. Eigenvalue problem, basis closely related to eigenvectors. Eigenvectors, basis. Yeah. All right. So let me carefully introduce the notation. Yeah, because here we use a lot of linear algebra notations. Yeah. Many of you, it's very likely many of you may get lost on these linear algebra notations. Yeah. So here, let me slow down a little bit. Yeah. First, eigenvector eigenvalue relationship representation. N eigenvalues, n eigenvectors. Yeah. So that's simple. Yeah. Yeah. So when we start, we have Then the corresponding solutions. After we have eigenvalues, eigenvectors, can we write our special Y solutions for that homogeneous linear system here? So here we only want to write homogeneous linear solutions for homogeneous linear system. Yeah. Yeah. So the corresponding Y solutions, Y sup k equals each eigenvector x sup k multiply e to that corresponding eigenvalue lambda kt, that function. That's the corresponding Y solution. How simple it is. So we can write n Y solutions in this way. N Y solutions. Oh yeah. Key assumption. I copy that condition. Okay. I copy that condition here. Yeah. Copy that condition here because we need to use that. Because we need to use these n eigenvectors. They are linearly independent. We need to use this property. And xk vectors, they are linearly independent. Yeah, we need to use that condition. All right. Fundamental matrix. We have this fundamental matrix concept we learned before. Okay? What's fundamental matrix? The capital Y n by n matrix, we just pack all n solution vectors. They are n solution vectors. We pack them in an n by n matrix. We call it fundamental matrix. That concept we used before. Yeah. Here we just bring it here. Okay? Yeah. Now, let's look at the relationship between Y matrix and the matrix formed by eigenvectors. Yeah. Matrix of eigenvectors. Yeah. Let's use capital X matrix represent n by n square matrix. We pack n eigenvectors inside this matrix. So we have this capital X matrix with all eigenvectors. Yeah. All right. Now the question. Yeah. Is this X matrix invertible? Invertible? Yep. So here. X is invertible. Why X is invertible? Because determinant of X not equal to 0. Why determinant of X not equal to 0? Because all the vectors, all the column vectors in this matrix are linearly independent. So here, this is a basic property in linear algebra. So you have a square matrix, okay? Square matrix. If you know all the column vectors are linearly independent, then the determinant of the whole matrix is non-zero, and the whole matrix is invertible. Yeah. All right, so that's one way. Another way, because here we look at the column vectors, right? You can also look at the row vectors. Yeah. If all row vectors linearly independent, then determinant non-zero, and the whole matrix is invertible. That's the basic properties in linear algebra. We can prove, but we don't have time to prove. Yeah. So we just use the result from linear algebra. Okay? All right. So invertible. Then relationship between Y and X. What's the relationship between Y and X? Each Y vector, X vector multiply an E function. Yeah. We need to write that relationship. Okay? Because Y, we can write Y vectors in this way. Okay? X vector, then multiply a scalar function, E. It's a scalar function. Okay? Then next, I split as a product of two matrices, I hope you can understand. You can see it. Right. All right. The question: how to see if these n y vectors are linearly independent? How to see that? Linearly independent. Because linearly independent, then we can write general solution. If they are not linearly independent, then we cannot use y vectors to write general solution. Yeah. So that's the reason it's important, linearly independent. But how to see that? All right. We see in this way. This Y matrix, from this structure, we can write it as a X matrix multiply a special diagonal matrix. This is a diagonal matrix. Yeah. Because diagonal matrix, you do multiplication, each entry you multiply to the corresponding vector in this way. If you use the matrix product definition, you can see that. You can see that. Matrix product, okay? The definition. Yeah. You can check that. Here, we're writing this way, diagonal matrix. Yeah. This diagonal matrix, we use the eigenvalues, E functions, eigenvalues. Yeah. Here, I want to introduce a capital lambda. Capital lambda represent this diagonal matrix. Okay? So X matrix multiply lambda matrix equals Y matrix. All right? That relationship. Yeah. That relationship. Yeah. All right. So now, determinant of product of two matrices. Now we want to calculate determinant of Y. Y equals X times lambda. How to calculate determinant of product of two matrices? Here, I give you a property. Yeah. Determinant of A times B matrices, product of two matrices, equals determinant of A times determinant of B. Yeah. Here, AB square matrices. If AB rectangular, then you cannot write this way. Okay? Here, we assume AB square matrices. So we can write in this way. Yeah. This property. Okay? All right. Now we apply this property here on Y. What is determinant of Y? Yeah. Wronskian. Yeah. Let's recall Wronskian. What's Wronskian? Wronskian determinant of Y. Okay? What's the Wronskian? Determinant of Y. That's the Wronskian. Okay? Yeah. So W of Y equals determinant of Y. That's the Wronskian of this linear system. Okay? Yeah. All right. So equals determinant of capital X times capital lambda. Yeah. Then equals determinant of X times determinant of lambda. Okay? All right. Yeah. And determinant of lambda, because it's a diagonal matrix, you just take the product of diagonal entries. The product of diagonal entries. And it is not zero, right? E function can never be zero. So determinant of lambda cannot be zero. Non-zero. Okay? All right. So determinant of X times E function, and determinant X non-zero, we already know it, right? X invertible, we already see determinant X not equal to 0. So determinant of X not equal to 0, then you multiply E function not equal to 0, so then determinant of Y not equal to 0. Determinant of Y not equal to 0, that means the matrix Y is invertible, and n y vectors are linearly independent. So we can use n y vectors as a basis of this homogeneous system. Basis of homogeneous system. Yeah. Try to understand on all these arguments. Yeah, quite a lot. Yeah. Yeah. All right, so get yourself familiar with these concepts. All right, that's it. So next time we continue remaining. Yeah, so we still will have a lot of materials from part C. Yeah. We just do 2 slides. Yeah. We have most part left the next time. Yeah. All right, yeah, that's it. Yeah, so one student chat message. Yeah, let me see what's there. All right, okay, yeah. Yeah. So the homework assignment, yeah, any question, let me know. Yeah, remember you have 1 day grace period. Yeah. So you have some breathing room. Yeah. But if you need more time, just let me know. Okay? Yeah. Question?
I probably need more time.
Oh, you need more time? Yeah. All right. I can give 2-day extension. How about that? 2-day extension.
Could I maybe use Friday? Because I have a test in another class Thursday.
Yeah. All right. Okay. Yeah. Friday. Yeah. Because if we still have that grace period, so then you can do Friday.
Yeah, that should help.
Yeah. 2-day extension plus grace period, 1 extra day. 2 plus 1. 2 plus 1. All right. Yeah. Yeah.